talking a little bit about the Green Bank Telescope. So I'll try to take it slow. Of course, you're welcome to try and ask questions during the talk, but as we all know, during Zoom, that can be a little bit challenging. So if I don't see your hand, don't worry, we will get plenty of time at the end of this for questions. And if I finish a little bit early, we'll just get to take a break a little bit earlier. So that's all good too. So with that, let me convince my screen to move. So this is the gist of what I'm going to talk about. So a little bit of history about the Green Bank Telescope and a quick overview of it, repeating a few of the things that Will talked about, and then going into details about some of the key characteristics of the telescope, and a very brief glimpse into the future, touching on a little of what Will did, but also some of the other projects that are ongoing. I will say that the primary goal of this talk is to make sure that as we come out of this, everybody has a good feel for the components of the telescope and kind of what makes it tick, so that as we go into the next series of talks over the next couple days, everybody's speaking the same language and understands when somebody talks about the feed arm or the this or the that, exactly what they're talking about on the telescope. So let me talk first a little bit of history. I think that's an important way to go. Since we're virtual, let me just point out this is where I'm talking to you from, is the center of that little star there, right on the West Virginia border, not too far from Washington, D.C. I will say the Green Bank was the first national observatory in the United States. It was founded back in 1957. And although we are Green Bank Observatory, that is our name, we are the original location of the National Radio Astronomy Observatory, which is our partner organization. So how we got here goes back to 1954. So back in 1954, radio astronomy was becoming a thing. Of course, Carl Jansky had been out there. We discovered the CMB. All of that had happened. And the world was taking off. The world was starting to understand that radio astronomy was an important aspect of astronomy and something we need to understand, something we need to study. And there had been a lot of people out there like Rote-Reaver and others that had built their own radio telescopes. And certainly Harvard, plenty of universities had. But the reality of it was that if we really wanted to become a player in the game of radio astronomy, we needed large and powerful telescopes. And in order to have a large and powerful telescope, the National Science Foundation was being asked, would you fund this idea of a national observatory where we could build large instruments that somebody couldn't afford to do on their own or within their university, and then make us competitive in the world? And what was exciting about this, which Will already touched on, is the idea that this observatory would be available to anybody that wanted to. Any qualified scientist would be able to come and use this telescope. You didn't have to be from a certain university or even from a certain country to do it. So that was back in 1954 at this conference. And at the same conference, they pushed it forward pretty quickly, and they came up with I think it was 20 different criteria of what would be needed if we were to select a site for this National Radio Astronomy Observatory they were talking about. And they had some pretty conflicting concepts. Like they said, you want to be near a large university and you want to be near your funding agency, near Washington, D.C., but at the same time, they wanted to be very far from civilization to keep the level of radio noise, the level of radio interference very low. And fortunately for us, that particular criteria really won out over the rest of them in a very far-seeing way, because as cities have grown up, this protection that we have living being where we are really helps protect us not just from things like the high tension power lines that they knew about back then and cars and things like that, but also just the Internet of Things that seems to exist these days. So you put all that together, and in 1957, October of 1957, they actually dedicated this site. So this was one of a number of sites that were chosen. State of West Virginia, as I'll talk about again in a few minutes, was very excited to have this, and so they did a few things to try to make the Green Bank site more appealing. And so here you can see the actual dedication of the Green Bank Observatory site, and on the table there is a model of the 140-foot telescope, which is intended to be the first telescope built on site. Due to some complications, it wasn't quite, but that was the idea at the time. So as Will's already shown you the slide, most of the slide, we are the original National Radio Astronomy Observatory, so we have all sorts of telescopes here, completed at a variety of different times. I do want to note that my slide is slightly different than Will's because we have two additional telescopes on site. The first one's down in your bottom left-hand corner. That's LOFASM, completed in 2013. It was run for a period of time and shut down, but it's back up and running again. We're excited to have that instrument. And then what looks like it's floating in space, sorry about that. I only realized it looked like that right now. Completed in 2022, up in your top right, that is the Chime Outrigger. So we have the CHIME array up in Penticton, Canada, and we are one of the outrigger telescopes to help them better fix where in the sky a certain source is. So a lot of historic telescopes, some still running, some still up, and then a number of new telescopes here and a few new telescopes coming online. So exciting place to be overall. Okay, so now let me talk to you about what I'm actually supposed to talk about, which is the GBT. Again, because you guys can't be here to see the telescope, which is really too bad, and I hope you come. This is a picture of what it would look like if you picked up the GBT and stuck it down in the middle of Washington, D.C., very close to the FCC, but not quite squishing them in case they still want to help us out with radio frequency interference. So 100-meter diameter dish. The GBT is the largest fully steerable telescope in the world. So it is not the largest telescope, it is the largest one that can actually steer around. It is also currently the largest movable structure on land. There are larger structures at sea than the GBT. So it's big, and I think you guys all know this why. The reason the GBT is so large is to give it its sensitivity, so it gives us a massive collecting area. As many of you probably know, with radio astronomy, we measure our units in terms of Janskys. One Jansky, named after Carl Jansky, the father of radio astronomy. One Jansky is 10 to the minus 26 watts per meter squared per hertz. The GBT often works in milli and micro Janskys, so all the way down to 10 to the minus 32 watts per meter squared per hertz. I'm going to focus a number of times on our radio quiet zones, and the reason for that is you really couldn't have a telescope like this working at the sensitivity it does without things like the radio quiet zones. Something like a cell phone on Mars, so just not talking like this alien is doing, but just going the "Hey, I'm here" signal, is about 1 million times louder than most of the signals we're looking at with the GBT. So again, the GBT big picture. We are a fully steerable telescope. That means we can go all the way down to 5 degrees above the horizon to observe. That gives us about an 85% sky coverage, and it means that we can even cover large parts of the same sky that, say, the ALMA telescope down in Chile can cover. So we have a nice overlap with them. We've got a nice, currently our range is from 0.3 to 116 gigahertz. The lower end of our frequency range is just based off of interest. It becomes impractical for a large telescope to go down to really low frequencies. You're better off building small arrays like low phasm. And the higher end of this is set by the atmospheric opacity, as you'll see in a little bit. We have an unblocked aperture. I'll talk more about that. It is one of the best decisions they made with the GBT and is something that is now being mimicked by many of the more modern telescopes that are coming online. And equally as importantly is we don't just go up to 116 gigahertz with a very large dish, but we also have incredibly good aperture efficiency. So even at 100 gigahertz in benign conditions, we have a 30% aperture efficiency. And in a typical year, we get about 6,800 hours available annually for observing because, of course, we can run day and night on the telescope. I say typical because we have been doing some maintenance, as Will already talked about with the painting and all. And so last year and this coming year are likely to be a little bit less, fewer hours, simply as we get the maintenance done we need to do to keep the telescope going. The science for the telescope goes all over the place. It is set by you guys. It's set by the proposals that we receive. But our more typical areas of science go everything from fundamental physics, looking at neutrons, stars, and pulsars and things like that, looking at stars, both the birth and the evolution. The origin of life, we do a lot of astrochemistry. We also have a good bit of our time going to projects like the Breakthrough Listen contract, where they're actually looking for signs of intelligent life out there in the universe. And then what we call galaxies across cosmic time. So that's studying everything from our own Milky Way galaxy all the way out to using Mustang to go look at the Sunyaev-Zeldovich effect of clusters of galaxies very, very far away. So very wide variety, and you'll hear more about some of that over the next few talks. The user community, you guys are the most important part of our telescope. We do that. We run the telescope. We build the instruments all for you. So in a typical 5-year period, we have about 3,000 individual scientists from all around the world proposing to use the GBT. Like I said, the span of disciplines ranges across the board. There's nothing to fix you into a certain discipline. If you have a great idea, you should absolutely propose. And probably the most important number is that bottom one. About 20% of the proposers are new every semester. So we really we hold these workshops to encourage people to think about ideas and to use the telescope. And we'll be spending a lot of time over the next few days teaching you guys how to use the telescope to help you write those proposals, but also to remind you that we're here to help you. So if you have a great idea, you can reach out to our help desk and say, hey, can the GBT do this? And we can work with you to see whether or not we have the instrumentation and the sensitivity to pull it off. Okay, so what is the GBT? When we talk about the telescope, I just want to step through the various components that everybody's going to throw around for you for the next few days. So just going from the top to the bottom of the telescope itself is has a primary surface, and we have a subreflector. So the photons come in, and they bounce off that primary surface there, and for the majority of the observations, they then go up to the subreflector and then down to the receiver room. So you're using the primary surface as your primary collecting area. The subreflector then collects all of that and focuses it down to the receiver of choice. We then, all of that subreflector and receiver room sit on what we call the feed arm. It's called the feed arm because that is where the feeds, the first parts of the receivers, sit on that. So the receivers are up on there and their feeds are up on the telescope. So that is the feed arm. Then that whole structure can tip on our elevation axle, so it tips up and down. That gives us one direction of motion, and then the second direction of motion is down on our azimuth track. So those are the main components of the GBT, and those are the ideas when you hear words from people talking about the components, that's what they're talking about here. So again, we talked about this. The telescope itself can go all the way down to 5 degrees, and you can see in the little cheesy little GIF on the bottom right, it doing exactly that. For observations, we can actually go slightly below 5 degrees if we have to, but we keep it to 5.5 to 5.2 degrees for observing. Can see 85% of the celestial sphere, and it's important to note too that we have a fairly fast slew rate, so we can go 40 degrees per minute in azimuth and 20 degrees per minute in elevation. It means you can move from one part of the sky to the opposite part of the sky, typically in less than 5 minutes on the telescope. This gives a lot of advantages if you have different sources all around the sky and you're trying to be as efficient as possible in your observing. So it allows you to pick and choose where you're going pretty quickly. So that's my quick overview of the telescope, just to give you a good feel for this. Again, you'll have copies of these slides, so if you want to remind yourself some of those keywords, you can go back and take a look at the slides there. So now I'm going to spend most of the rest of my time talking about the key characteristics of the telescope and just stepping you through some of the features of it, and some of the things that makes the GBT unique and why you would want to turn to the GBT for your science. And then finally, again, look into the future. So the optics of the telescope. The GBT is a 100-meter diameter effective dish. It's actually slightly larger than that. And it is the subset of a parent parabola that is 208 meters. So remember with the way you think about your optical focuses, when you think about your light rays, you can focus to a particular point if you use a parabola. If you have a sphere, you focus to a line. So we are focusing to a point, our subreflector or our prime focus receivers, I'll talk about in a minute. And so that is why we are part of the parent parabola. And you can see that on the right where the feed arm is located is the focus point of the parabola, so that those two images match up with each other. The telescope, as I've said, as Will has said, and as you'll hear over and over again, is got an off-axis design. This means that we have no structure whatsoever blocking the photons as they're coming in, and this gives us an absolutely phenomenal dynamic range for the telescope. If you want to see what I'm talking about, on the left is a traditional telescope design, so where you have your 4 struts coming in to hold your receivers over the center of the telescope. And below that is an image of a source, unprocessed data coming in, and you can see the difficulty with dynamic range. You've got a lot of noise sitting there where the brightness comes in and it spills over and decreases your dynamic range of the structure. On the right is an unprocessed image of the same source using the GBT, where here you can really see how the lack of scatter from the structure dramatically increases the dynamic range of the telescope. And so it's really a fantastic mapping instrument to go and look at things for diffuse gas around bright objects, for example. So I've talked about the subreflector. It's an 8-meter subreflector. It can twist and turn, has 6 degrees of freedom, and that's something that you actually take advantage with at some of the higher frequencies where you'll nod the subreflector as you're observing. I should add, though, that we also have the ability to pull what we call the prime focus boom out in front of the subreflector. So as you go to lower frequencies, the frequencies are so low that the subreflector itself would be what we call over-illuminated by your photons. That is, it's too small to efficiently collect photons at the long wavelengths. And so to compensate for that, when you're working at those lower frequencies down below 1 gigahertz, we actually will swing a subreflector out that has a receiver, or sorry, swing a boom out that has a receiver on it, and that will swing out in front of the subreflector and collect the photons directly from the primary dish itself. So again, these are the prime focus feeds that you'll hear about. Those are all typically below 1 gigahertz. The one exception for that is our ultra wideband feed that I'll talk about a little bit at the end. That one is going up there simply because of the wide range it has. It needed very large collecting area, and at its lowest frequencies, it too would over illuminate the subreflector. Other key characteristics about the GBT, what makes it just a fantastic instrument to use is its active surface. So the GBT has more than 2,000 individual panels that create that primary surface of the telescope. And at the corner of each one of those panels, we have a subreflector that acts on the 4 corners right there. And those actuators can do 2 things. At the low frequency end, they simply compensate for the sag of the dish due to gravity. But at the high frequency end, they are actively working to keep the dish in focus, so at the correct shape, so that you can observe all the way up to 116 gigahertz with that 30% or well, 20% aperture efficiency at 116 gigahertz. So this gives us an incredible surface RMS of about 2.3 microns, which is the equivalent of about 4 human hairs across the entire 100-meter surface. So this is why we can go to those high frequencies, and it's really been a fantastic boon for us that they've done this. How these things work is it's a system that actually uses a temperature sensors that are scattered across the structure of the telescope. So those are measuring the temperature of the steel on the telescope. Those are feeding that into a model then that we have developed that actually says, you know, when this temperature sensor measures this and this one measures that and so forth, this is what you need to do in order to keep the dish at its optimum shape. So that's the idea for the open loop system. We add to that the idea of holography. So traditional holography is when you're measuring the entire surface of the dish in focus. We do that a couple times a year to make sure our model is as best as it can be. But then we also have the idea of out of focus holography, which can be used very quickly. So when you're running your high frequency observations, you will be running out of focus holography observations that can very quickly measure the rough offsets of the dish and give you a correction. So it's very similar to when you focus the telescope, you know, you do a quick focus correction that feeds into the focus model just like it does with optical telescopes. The out of focus holography system feeds into our surface model to allow you to have the optimum surface. How often you have to do those corrections depends on 2 things. It depends both on what you need for your sensitivity and also on the observing conditions. So if you're observing in a situation where the the structure is heating and cooling rapidly, you'll need to do this more often. If you're observing in benign conditions, say around midnight, you don't need to do this nearly as often. And they'll talk to you more about this as you get into some of the high frequency observing lectures. Okay, finally looking at the frequency coverage of the telescope, we cover from, as I said earlier, 0.3 to 116 gigahertz. So that allows us to cover the entire frequency of the Jansky Very Large Array, as well as hitting the lower frequencies of the ALMA telescope. So that way we can work with our partner organizations and provide the zero spacing for those instruments. When you actually look at the system temperature of our receivers, you can see that in this plot right here. Now, I should say I stated we cover from 0.3 to 116 gigahertz. It is not contiguous. We do not bother to put a receiver at 60 gigahertz. The reason for this is just that the atmosphere is completely opaque. And so you wouldn't be able to see anything anyway. So we don't cover that area. We have our Q-band receiver that goes close to, goes into 55 gigahertz, and then we have the W-band and Argus receivers that come and pick up after the atmosphere starts to lose that opaqueness. As Will already talked about, most of the receivers we have are either single or dual pixel receivers. So that is at the lower frequency end, down up through X-band, so up through 12 gigahertz, we have single pixel receivers on the telescope. And then when you go above 12 gigahertz, starting with the KU band receiver on up, the majority of our receivers are 2 pixel. That allows you to nod back and forth as you're observing and both monitor the atmosphere while keeping the efficiency of your observations very high. We do, however, have 3 multi-pixel cameras on the GBT. So this is the K-band focal plane array. This is our first multi-pixel camera. So this is literally just a grouping of 7 traditional feed horns that are packed together. And you can see them on the left-hand side there. And then up at the higher frequencies, we have both the Argus instrument and Mustang 2. Argus is a spectral line instrument. We'll already mention it. It has multi-pixels, 16 pixels packed up on the sky, going from 74 to 116 gigahertz. It is a single polarization spectral line receiver system. And then we have the Mustang 2, which is a bolometer array. So this is a total power receiver that has 223 feed horns that mix together onto the telescope. And it is by far the most sensitive instrument you can get right now at that frequency range. So how do we pack all these receivers together? The idea is we have a rotating turret with 8 different receiver holes, so we can, at any time, 8 of our 11 receivers can go up onto this turret, and you can, when you get onto the telescope, you can spin this turret to pick the receiver of choice. It takes anywhere from about a minute to 4 to 5 minutes to go between receivers, just depending on what needs to happen there. So that's where the bulk of them are. You can see here on the left, this is what it looks like if you're standing looking down onto the receivers. So these are, in some cases, receivers, a couple empty holes there, with their covers on. And then if you were to go into the receiver room itself, this is what it would look like inside, where you have the receivers feeding down into a variety of different receiver boxes on the telescope. And just for scale, you can see one of our engineers in there working on the receivers. Then, as I mentioned earlier, we also have the prime focus system. This can only handle 1 receiver at a time. We currently have 4, soon to be 5 receivers that can go up there. And so we have to switch between those. It takes anywhere from 4 to 8 hours to switch prime focus feeds up there. And so we have to build a schedule based off of receiver pressure to decide exactly which receiver we're going to have in the prime focus boom at a time. So those ones we can't switch back and forth. Then this leads to a lot of the interest in the ultra wideband receiver because it will cover all of those frequency ranges quite well. Okay, finally moving into just the signal processing, we talked about the telescope, and we talked about the receivers on the telescope. And so that's the receivers and the receiver room that I just showed you are the first 2 boxes here, first 3 boxes here. So you've got your feed itself. So to go back to this picture, if you look on the left, you're looking at the feed. That's the brass piece. And if we didn't have Teflon there to protect it, you would be able to see into that feed. So that's the feed. And then the photons go from there into what we call the cold electronics. So this is where we have things cooled down to anywhere from about 2.3 all the way up to about 8 to 10 Kelvin, where the photons are coming in and they're being processed inside of it. And those 2 pieces come together, and that's your receiver. So when we talk about a receiver, it's both your feed and your cold electronics there. Then from those cold electronics, we will actually bring them over into warm electronics. And this is the place where we'll take the signal and we'll actually process it by the same electronics for quite a few different receivers there. That allows us to take this down, and we'll actually change the frequency of them to allow us to send the signal down the signal distribution path all the way to the Jansky lab. So you've got your feed, and your cold electronics is the receiver. You add that to your warm electronics, you've got a front end. You take all of that to a signal distribution piece, and that's what we have up in the receiver room. And for the GBT then, that signal goes down 1.8 kilometers of fiber from the telescope itself to the control room and the electronics in the control room, which is in the Jansky lab, which is where I'm talking to you from right now. And so once it gets to the control room, we do a little bit more signal distribution so that we can send it to the back end of your choice. That back end will then do the final processing and bring it to the computers so you can actually look at the signal itself. So if you want to think about this from this simplistic diagram into words, you can take the same idea. So the antenna itself gathers the radiation. The front end and receiver system takes that and converts the signal from a free space photons to an electrical signal. And then they amplify that signal so that it can get passed all the way down to the final signal processing system. So if we don't amplify that, it'll actually decay away before we get to see it. We then use what we call the IF, the intermediate frequency system, typically to mix the signal to convert it to a different frequency and transfer it to the back end, and then we send it down and measure the signal in the back end. That is the typical process. I will say that we do have one receiver up there right now, Mustang, which bypasses that IF system. It actually digitizes the signal right at the front end and then passes that on down. So this is the typical path you'll be hearing about, but there are some exceptions in there that people will talk about when they talk about individual instruments. So, okay, so that took us, we went from the antenna, we looked at the signal, we went through the receivers, we went through the IF process, we went through the IF chain, we passed it all the way down to this building I'm in here, the Jansky building, and then you have to pick your back end that you want to use to actually process your signal. So that we have three main backends that are used by the GBT, Vegas, the DCR, and the Mark 6. Vegas is our primary pulsar and spectral line backend. It stands for the Versatile GBT Astronomical Spectrometer. See if you can remember that name. We can quiz you at the end of the week on that. It has many, many modes to choose from, so you can kind of pick and choose what the best situation is for you. Do you need very wide bandwidth? Do you need high time resolution? Do you need high frequency resolution? You can even take it and take the various components of Vegas and spread them out so they don't have to be contiguous. And you can have up to 8 spectral windows looking at different spectral lines across the bandwidth that's available for you. So it's an incredibly flexible instrument. And it's not uncommon, to be fair, when you propose, you'll think, okay, this looks like the Vegas mode that I want to use. And if your proposal gets accepted, your proposal friend might come back and suggest a few different modes. It's a complicated instrument, and that's okay. You know, put your best guess into your proposal and don't worry if somebody comes back and talks to you about different ideas, just to try to maximize the use of the instrument. It's quite flexible. Almost everybody will also be using the DCR. This is the digital continuum receiver. It's occasionally used for actual continuum total power measurements for science. Single dish telescopes, for a whole bunch of reasons, aren't optimum for total power observations, and so it's not commonly used for that. But it is used by almost everybody for pointing and focus observations. So when you first get on the telescope, you want to make sure that the pointing model is good. You want to make sure that the telescope is focused. You'll use the DCR for that, and then switch to Vegas or the Mark 6 back end. And so finally, Mark 6, this is a VLBI recording system. That is all it is typically used for in Green Bank. So this is a disc-based recording system. If you're doing, for example, observations with the high sensitivity array, which involves the GBT as well as the VLBA, you'll take the data with the Mark 6, and then that disk is quite literally shipped to Socorro, where the disk correlation is done. Those are not the only backends available. Those are just the primary ones. We have 3 others. This includes the CCB. This only works, with the KA receiver, not the KS receiver, the KA receiver. You'll use this if you're observing at high frequencies and you want to do out-of-focus holography. You'll often use the CCB. You can, of course, also use it as intended with the KA receiver for science. We have a radar backend. This is used exclusively when the GBT is receiving radar signals from the Jet Propulsion Laboratory, typically. And so this is the backend for that. And then we have the Breakthrough Listen backend. This is an incredibly high time and frequency resolution system that has been developed and is proprietary by the Breakthrough Listen team. But they do allow people to propose to use this instrument. You have to ask their permission before you write your proposal. And so it's a specialty instrument. It's described online as you go through our documentation, and it is available for use, but be aware that it's a limited use situation and you do have to get permission to use it by the team. Okay, so that was the entire telescope. That was a lot. Talking about the telescope, talking about all of its characteristics. But I mentioned at the beginning that I would be remiss if I didn't also talk to you a little bit about the radio quiet that we have here in Green Bank. This to me is, although it's not a feature of the telescope per se, it is an important characteristic of the observations that you'll be doing because it allows you to observe things in Green Bank that you can't necessarily observe anywhere else in the world because of the radio quiet. So, to go all the way back to the beginning of this talk, way back when 1954, when they were talking about the fact that the U.S. needs this idea of a national radio observatory, they had picked a number of different sites. The state of West Virginia liked the idea of being one of those sites. Yeah, they knew that they had identified actually two locations in West Virginia, and so the state of West Virginia proactively passed a law stating that in 1956, saying that if you build a large radio facility here, we will provide state-based protection for that facility within 10 miles, 10-mile radius of the facility, which will protect it from any interference whatsoever. So that's the West Virginia Radio Astronomy Zone. By 1957, as the site had been picked, the FCC and NTIA, our federal regulators for spectrum, came out and created this idea called the National Radio Quiet Zone, which is a 13,000 square mile region centered between Green Bank, West Virginia, and the Sugar Grove Research Facility, which is also in West Virginia. So what's the difference between these things and how do we deal with them? The West Virginia Radio Astronomy Zone is, of course, much smaller, 10-mile radius around the observatory, but the protection is incredibly powerful. It protects us against any electrical equipment that causes harmful interference. So that means it protects us from everything from electric fences that have gone bad to any type of cell towers or home systems that might cause interference to us. It protects us against all of that. We can go out, work with the community to shut down any of those systems. So incredibly powerful protection for us. And this is a state-based protection, so it's actually the sheriff's department that would come in and fine somebody if we ask them to. Then there's a much larger protection called the National Radio Quiet Zone, and this is that 13,000 square mile region centered between Greenbank and Sugar Grove. You can see it on the map there. So the southeastern corner is, sorry, the eastern edge of that is all the way over at Charlottesville, where just past our headquarters. The western corner goes pretty far out to the west, out to Richwood and that area. Very large area. And this protects us against all fixed and licensed transmitters. So this is cell towers, this is radio stations, this is anything along those lines. And so what happens is when somebody requests to get a license from the NTIA or the FCC, that license, if it falls within the National Radio Quiet Zone, gets passed to us, and we look at it to decide if the transmitter that they want to put in is going to cause a problem for our telescope. So it's not that within that region there aren't plenty of cell towers, it's just that all of those cell towers have to be pointed away from Greenbank and Sugar Grove so that they don't interfere with our operations. So it's been a really powerful protection, and the fact that it's such a large area has really helped us out a lot, keeping the radio quiet. Okay, so that is, in 35 minutes or less, a quick overview of the telescope and its key characteristics. So again, to remind you, the key characteristics, the optics, the frequency coverage, the signal processing, and by no means don't forget the radio quiet zones that we have here. So I'm just going to take the last 5 minutes or so and just talk to you a little bit about the future of the telescope and some fun stuff that is coming online very, very soon. So looking at to the future, some new instruments, some new ideas. First off, and Will's already talked about this, this is the ultra wideband feed. This is a 0.7 to 4 gigahertz feed. It's being optimized for pulsar work. In fact, it's being optimized specifically for timing the nanograph pulsars. They are the ones that got the funding initially for this instrument. So that is its primary goal, but that doesn't mean you can't also do spectral line observing for it and other types of pulsar timing with this instrument. Its aim is a T-sis of about 30 degrees, and it will, because of the wide bandwidth that it can observe all at once, it will double the sensitivity for a lot of pulsar timing observations by doubling the available bandwidth and keeping the system temperature quite low. So the instrument is in commissioning right now. It actually was just up on the telescope last week for some measurements and is now in the lab for a little bit of amplifier work and a few other things, and is going back up hopefully early next week for the next and possibly near final round of commissioning for the instrument. So it's going to be a really exciting addition to our pulsar observers, but also an exciting addition for anybody that might be looking, for example, for radio recombination lines or something else, where having the wide bandwidth at those frequencies is quite useful for you. So anybody will be allowed to use this instrument and propose for it as soon as it's fully commissioned. Hand in hand with what we call Uber, the ultra-wideband receiver, is the looking at some of the ideas, for example, at digitizing the IF, the radio, the intermediate frequency band. So instead of taking the signal in by receiver, so you have your receiver taking the signal and then transferring it to an intermediate frequency and passing it all the way down as an analog signal to this building here where the final processing is done. The idea is that what if you could instead digitize the signal all the way up near the receiver itself? And there's incredibly good reason to do that. Basically, you get a far more stable baseline when you do that. You can increase the range of frequencies detected at any time, and you can even do things like active RFI mitigation, things like that. So it's an exciting idea to go out there. The goal is to try to deploy it. It's been challenging. When we looked into this 20 years ago, there simply wasn't the type of digitization available to make this happen, and now that's no longer true. So that is also being looked at. Um, Moving away from those systems into what Will's talked about, the radar system. He spent some time on this. That's because Will's on that project, so he knows more than I do, frankly, about it. But this is a really exciting idea. This is a concept that we've been kicking around for about 10 years now. The intent was to be a complementary system to the Arecibo radar system. So Arecibo had a very strong S-band radar system. It was fantastic. We started testing this when Arecibo was still around. With the demise of the Arecibo system, this project has become ever more important for astronomers. So the goal here is, again, to ultimately get a high-power radar system on the GBT with GBT transmitting and the VLBA, and ultimately the next generation VLA is the receive system. So that's all underway. That's not fully funded, although it's funded for some of the preliminary work. But in the meanwhile, we do have this low power system that has been going up onto the telescope and will be going back up again fairly soon. So that's an exciting thing. And it's a few years down the road before we get to see the really high power system out there, but we're getting some pretty fantastic results in the meantime on this. And then the last thing I just want to mention really quick on this is we're also working on a few other ideas, including, for example, trying to double the bandwidth of the receiver. So when you think about something like Uber, and you want to look at Uber and you want to try to say, well, I want to take advantage of the whole system or W-band or anything like that, we're in the process of running some demonstrations to try to understand what it would take to increase the instantaneous bandwidth on the telescope, and to try to go out and to try to say, well, if you want to look at HCN lines and a few other transitions, you might be able to look across, instead of just 8 gigahertz as you can now, maybe 16 or 20 gigahertz. So we're playing with a lot of those ideas, but what it's really going to take to decide where to go next with the GBT is people like you guys. So we really need to hear from our user community when you're thinking about the science that you can do with the GBT now. That's fantastic, but also think about the science that you hope to do with the GBT, that you would like to be able to do with the GBT. And it's the user community that's going to help us try to decide where to throw our efforts, where to throw our time, and what instruments we want to go to. Will showed you things like the next generation Argus instrument. We've talked also about next generation Mustang instrument. And really the idea is what the user community wants. Once we know that from you guys, we can start thinking about how we would fund that and where we would go. And so with that, I think I am done now and happy to take any questions people might have.